All right, let's get started. So last class we talked about the limitations of circuits. Right. So in particular, we showed that even though Boolean circuits and NAND circuits and any other class of circuits which can compute every function, they are limited in that some functions require a lot of resources. Okay. Some functions indeed require almost an exponential number of gates. There is no way to go around it, right? That was one of the things that we discussed. And this was Shannon's theorem. Okay. And the proof of this had two sort of key ideas. One is to encode circuits as strings. And the other one was to count by encoding. Okay. So one of the things that we discussed was, okay, we wanted to count how many Boolean circuits there are. And since we already had an encoding, we could easily get an upper bound on this by just counting the number of possible distinct strings, right? So this idea of counting by encoding actually shows up in many other places, even in my own research to this day, and many important results in algorithms, complexity, and also in pure math in many other places. Okay. So today our goal is, I'll first quickly review the big steps in Shannon's theorem. I think just in terms of the number of ingredients involved and the length and the impact, this is one of the more complicated theorems we'll prove. So it's worth just going over sort of the big steps that we went over last lecture. And then we will look at another implication of circuits, of encoding circuits as strings, which is to universal circuit. We'll define what this means is, what its implications are, and then hopefully today or maybe in the next lecture, we'll move on to our next model. Okay? All right. And before I start doing that, just want to remind you that homework 1 is due today at 9:59 p.m. Okay? So make sure you follow the deadline on Gradescope so that you can submit it. All right? Okay. All right, so let's see where we were, right? All right, so this is Shannon's theorem. And just to contrast, what this is saying is, some functions need gates. And imagine, this is the number line, 2 to the n over 24n is sitting somewhere on this line, right? And we showed in class that every function can be computed with roughly 2n times 2 to the n gates. Okay, so every function can be computed with at most 2n times 2 to the n gates. And I stated without proof that in fact this can be improved to something like 2 to the n by n. Okay, something like, let's say, 10 times 2 to the n by n. Okay, this was stated without proof. Okay, so every function can be computed within some constant times 2 to the n over n, whereas some functions really sit in this sort of green area. Like you cannot go below this. Okay, that's what it means. There are some functions here which are very hard to compute. Okay. All right. And the proof, as we said, involved the fact that, okay, the encoding thing. So we have an encoding E from all circuits which have n gates, m output bits, s size at most s to 0, 1 star, where for every circuit, the length of the encoding is at most some, like, let's say 12 times s times. Okay. All right. So this was kind of the key ingredient that went into the proof of Shannon's theorem. And now we are going to explore another very important application of this fact. Okay. All right. So what is this other application? So once we have a circuit itself denoted as a string, the next thing that we can do is to give the string itself as input potentially to another circuit. Okay. So we're going to manipulate circuits now by using other circuits or functions. Okay. All right. So in particular, I'm going to ask for something like this. So I'm going to define a function which we'll call eval, and it will show up again later on. So it is going to take some input x as part of its input and a circuit. So let's say it's an AND circuit. Okay, you have some circuit, whatever this diagram is. Let's say I draw one more NAND gate here. Okay, so I'm looking at circuits itself as data now, right? So someone is going to give you the description of a circuit. Okay, here's a paper diagram of what the circuit is supposed to do. And here's the input X that I want you to run this circuit on. And your goal is to tell me what the output is. Okay, so you're taking the description of the circuit and an input for that circuit and giving me the evaluation of the circuit on the input. Okay, so a little bit like what you do when you're executing a program, right? So when you're running a Python script with some input, what you're really doing is you're giving the description of your code as a text file along with the input that you want to run your code on to the compiler or the executor, right? And it runs the program on the input and gives you the answer, right? So we're asking for something similar here. I give you the circuit and an input X, and I want you to, okay, tell me the value. This seems kind of, circular or useless. Right? We said circuits themselves were designed as a model for computing, But now I'm saying, okay, I need something else to simulate or evaluate circuits. Okay? But nevertheless, we'll see that this can be very useful. Okay? So let me be more precise in what the goal is. I said it's important to come up with the right definition. And I'm going to define a new function, which I'll call eval. And it depends on 3 parameters. For each nms, you get a different function. Okay? So eval or evaluator is a function which takes okay. So whatever this number is, let me just call it size of nms. Okay? And yeah, so it doesn't quite matter what this exact exact number is for now. Just think of it as some number. Okay? It is a string of length at most this much, and another string which is supposed to be the input x, right? And it gives me an output which is m bits long. So the way to interpret this is the first part is the description or encoding of a circuit with n inputs. With n inputs, m outputs, and s gates. Okay? And the second part is just the input x. All right? And I'm going to define eval of c comma x is c of x if c is a valid circuit and 0 to the mths. Okay? So here, there's some small technicality that when we define this encoding, every circuit, every valid circuit gets mapped to a Boolean string. But not every Boolean string has to correspond to an actual circuit, right? So for example, when you look at Python programs, every program is kind of a proper text file, but not every text file is a valid program, right? So I can, to the compiler, I can give any text file as input. I can say, okay, here's my Python program, run it, but it might not be a valid program, and it'll throw an error. Okay? So here, we're just saying, if it is a valid circuit, you have to tell me what's the value that you would get from evaluating the circuit on the input x, and otherwise, as a dummy placeholder, give me 0 to the m. Okay? Is the definition of eval clear? It's really just like a compiler or interpreter for circuits with n variables as input, m output bits, and s gates in total. And the reason it's well defined is because we have a proper encoding, right? So the circuit itself is defined by a Boolean string, so that's what it's taking as input. All right? Okay, so we define this evaluator function, but why is it useful? Well, here's a mini meta principle that you can formulate. Eval itself is some function, but we know that every function can be computed by a Boolean circuit, right? So in other words, there is a Boolean circuit that computes eval and ms. Okay? There is a Boolean circuit. There's a single Boolean circuit which can actually act as a compiler or interpreter for all other Boolean circuits up to a certain size. Okay? Why is this theorem true? I mean, just as a first guess, any suggestions? Why should this be true? Any guesses? My claim is that actually we've already shown this. We don't have to do anything from scratch. Why should this be true? Why should eval itself be computable by a Boolean circuit? Yeah? Exactly, right? So, I mean, right now, eval is just another function, right? So we know every function has a circuit. Implies eval itself has a circuit. Okay. Of course, the size of the circuit can be vastly inefficient, but that's okay for now. Okay. So what does this look like? Meaning, I can write down a single circuit. So let's say you're a chip manufacturer. You say, okay, it's very hard for me to keep rewiring these things every time. Wiring requires soldering or doing some other connections. I don't want to redo these connections every time, right? So changing inputs is much easier than rewiring things, right? So what this allows us you to do is to say, okay, I can build a single circuit. You just tell me the number of variables, the number of output things, and the number of gates you're going to use. Okay? And the inputs to this are of two categories. Right? So one is, maybe 0, 0, 1, 0, 1, 0 something. So this is the description of the circuit. Okay, and then this is X input. Okay, conceptually it's a very simple idea, but practically it's very, very important. Okay, so what are we saying? Somehow there's a single circuit where it has two kinds of inputs. One is the description of the circuit, and then with the actual input X that you want to evaluate on. And just by changing the values on the top, I can mimic any other circuit. Okay, so imagine I print this circuit out. This can mimic addition circuit by, for instance, changing these things. It can potentially compute multiplication by just changing this. It can compute any other thing that you want only by changing the inputs, and you don't have to rewire everything. Okay, and the output will be C of X. Okay, any questions about this statement? And why it might be useful. So basically, this is how, in some sense, modern computing works. So you're not going to manufacture a different circuit each time you want to change your computational task. You have the same hardware, but on the same hardware, I can replicate or simulate any other circuit that I want. And the reason for that is that we can compute this evaluator circuit. I'm just going to hard code this particular wiring for eval, and then mimic any other circuit by only changing the inputs. Okay, does it make sense? Yeah. So X is the input for the circuit C, right? So you have a program and you have an input on which you want to evaluate the program, right? But now there's a compiler which takes these two as input and gives you the answer, right? So that's what eval is doing. It takes the description of the circuit and the input X and runs the circuit effectively on X and gives you the answer. Exactly. Yeah. So let's say I want to compute. Now maybe someone says, okay, compute add of 1050 Okay, it should be in binary, but let's say that's not binary either. Okay, so then this would be X, and I need to write down the circuit for add and put it in here, right? And if I want to do mult, let's say, same thing. Now this would be X, and I would put the circuit for mult in here. Okay, if you're familiar with something like FPGAs, this is basically what's happening there, right? You have the same underlying hardware, but by programming them, you're changing what circuit you're actually implementing, right? And here the programming just comes down to toggling these bits in a specific way. Okay? All right. So yeah.
By description of circuit C, is that the description of what gates are?
So the description is what we already constructed from the encoding, right? So in last lecture, we showed that any circuit can be encoded as a Boolean string, right? So we have to fix on that encoding. Okay, so we are using that critically here. Okay, so that allows us to manipulate programs more or less. So that's kind of the meta idea, which is very important. Much of modern computing, I mean, the reason we have general purpose computers is to some extent this theorem. The real reason will come much later in the class. Similar principle, but a more meta level. Okay, so we're building one circuit to kind of mimic all other circuits of certain size. Okay. Any other questions? Okay, so this is already very interesting. But if you recall, the general purpose theorem was quite inefficient, right? So if we use that, you would end up saying to simulate a circuit of size S, I might have to use way more gates, right? I might need exponential number of gates. So even if I have a general purpose computer or general purpose circuit, if it's very big, it might not be very useful. Okay? But this is important enough that people have figured out exactly how well you can evaluate evaluator. Okay, so what's the best possible circuit for eval, right? So remember in the previous lecture, I said, okay, the general purpose theorem says that every function has a circuit of size n times 2 to the n. But for some specific functions, we can get much better circuits. Like if you're interested in addition, I can get a circuit which only uses a linear number of gates. If it's multiplication, I can even use grade school multiplication to get a circuit which has only quadratic number of gates. Okay? And it turns out for eval, you can get a circuit which is similarly super efficient. And this is something that we are not going to prove. It involves a lot of care and many ideas. And there exists a circuit, let's say a NAND circuit even, for eval NMS of size O of S log S. Okay, so let's say I'm interested in S greater than or equal to N. Just to simplify the parameters, let's say the number of gates that you actually have is more than the number of inputs. It's not a very strong assumption, just prevents me from having 2 extra parameters around. Otherwise, we can even get a more precise statement. But this is saying there is a single universal circuit which can simulate all other circuits of size at most S with only a logarithmic overhead. Okay? And we are not going to prove this. And this was first shown by Valiant in 1970s. Okay? The text has a proof of this with something like O of S times log squared. But you can actually do even better. S log S is possible. Okay, so what does this mean? So let's draw a picture again. So we are looking at circuits which have, let's say, a million gates, S gates. So each such circuit can have completely different wiring, right? But we are saying I can build a single circuit with S times log S gates, right? So if S is like a million, then log S is like what, maybe 10 or maybe 15. So it's saying roughly for 10 times S many gates. Well, okay, let me not. So let's say as an example, S is 2 to the B20. Okay. So then it's saying there exists a single circuit with roughly 20 times 2 to the 20 gates that can mimic all size less than or equal to S circuits. Okay. With a slight overhead, with only logarithmic overhead, I can build a single circuit which can mimic any other circuit just by toggling the inputs in a specific way. All right. So if you were a hardware manufacturer and you had to build something to simulate all circuits up to certain size, you should really just put down this generic circuit for eval and let the other people reprogram it by setting these bits and then capturing any other behavior. Okay. Any questions about the meaning of this theorem? All right. Okay. So as I said, this previous thing is what I call a universal circuit or a meta evaluator. Right? So we started with circuits as a model of computing, but now we are saying a circuit itself can evaluate all other circuits in a very efficient way. Okay? And this universal circuit, as I said, is very important in programmable hardware, for example, and cryptography, for instance, and many other places. Okay, this is effectively programmable hardware because I'm setting up a single chip, and then you can program it by toggling these blue bits and then mimicking any other circuit. Okay. Any questions about the statement? All right. Okay. So let me summarize what we learned about circuits quickly, and then we will go on a little bit of a philosophical tangent and then come back to actual concrete stuff. All right. Okay. So we saw that circuits can be implemented as physical devices. Okay. So this was one of the starting motivations for defining Boolean circuits or NAND circuits, right? So these were simple operations, and the reason we picked these simple operations was, okay, you can actually realize them using physical devices. Now we saw some fun things like using fluid for it, but the real world, you would use semiconductors for it, right? If you can build an AND gate or OR gate and NOT gate, then you can do everything else by wiring them together, okay? The next important point about them was that every function can be computed by Boolean circuits. Okay, hence also by NAND circuits. So as a model, it is very powerful. They can actually compute almost everything that we want. All right. So they can compute everything, but at a cost. Okay, that was the next thing that we saw. So some functions require exponential size circuits. As good as this model is in terms of being able to compute everything, the amount of resources you need might grow exponentially for some functions. Okay. And lastly, we can have very efficient universal circuits. That can compute eval. Okay. I would say, in some sense, these three properties, one, two, and last one, are critical for a model to be useful. Okay. You want it to be physically realizable. You want it to have enough power to compute, everything, right? And the last part is saying I don't have to start from scratch every time, right? If you have to rewire for every operation or every function that you want to compute, it's not going to be useful, or at least as useful as you would want it to be, right? Whereas the universal thing says, okay, you just build this one chip, this one specific wiring, and I don't have to touch the wires ever again to recompute a different circuit. I just have to toggle these inputs, and that's it. Okay, that's really magical. And the fact that you can do this so efficiently with only logarithmic overhead is what makes Boolean circuits and circuits as a model very useful in practice. Okay. Any questions about these points? Okay. You have a question? Okay. All right. So the last thing I want to say is, these points should already be convincing, but there's also a belief. I should say belief. It's not a theorem or a conjecture, but it's a belief in computer science and in physics, really, that circuits are as good as it gets. We'll call this the physical extended Church-Turing thesis. Okay, or PECTT. Okay. So it says that if a function f, let's say we're only interested in 1-bit output functions, can be computed by using S physical resources. So if a function can be computed by using S physical resources, meaning whatever, maybe you're using fluids, maybe you're using atoms, you're using whatever crazy physics that you want, chemistry, whatever, right? The belief is that then it can be computed by Boolean circuits that use roughly S gates. Okay. So it's a hypothesis that Boolean circuits are basically as good as it gets in terms of being realizable in the physical world. Okay, this is a hypothesis. This is some statement that we think is true about our natural world. no matter what physics theory you use, if you're using S amount of physical resources, it should be possible to achieve the same computation using roughly S gates. Maybe you'll change something in the constants, but other than that, you're not gaining too much efficiency. Okay? You're not going to suddenly go from using 1 million gates to like 10 gates by changing the model of computing. That's what this hypothesis is saying. Technically, it's already false. We will see a correction to it later on, which is that if quantum computers exist, then as stated above, E is false, okay? But not in the sense that it is false as stated, but it becomes true if I just allow one extra gate operation, right? So it's false if I only allow you and, or, and not, but we believe it gets fixed if I allow you one extra gate that we'll talk about towards the end, okay? But even with this, people have come up with all kinds of crazy theories to defeat it, but no one's found something which is still plausible. For instance, here, there's an experiment where if you think of minimum spanning tree problem, right? If you know what that is, it's a problem in graph theory. It's an important algorithmic primitive, and you can write an algorithm for solving it. Right? But then at some point, physicists observed that maybe soap bubbles apparently solve the minimum spanning tree problem very well. I just put some pegs in the position of the graph, dip it in soap, and come out, and it comes out to be some spanning tree problem, and so on. Okay, so is it violating the physical extended Church-Turing thesis? Because in some sense, dipping and taking out is not taking as much physical resources as running the thing for so and so long time, right? So what's the catch here? Where is or is there any deception here, or is this violating PECTT? What do you think? Okay, so they're cheating a little bit. So how are they cheating? Take a guess. We'll see if it's correct or not. Yeah? You want to take a guess? Okay, so the answer is that someone has to tell you where to put the pegs, right? How do you know where to put the pegs? They're not just part of the input. You have to put the pegs in a very specific way so that when I dip it in the solution and I take it out, I have this minimum spanning tree sitting there, right? Someone has to tell you where to put those pegs. And who is telling you that? You have to do some computation to decide that. And that's where the catch is, okay? And people have looked at something called DNA computing, right? Where, this is also real. People are there is some practical work on storing stuff using DNS, just as we use, we really think of it as chemicals, right? So if you think of a flash drive, at the end of the day, it is being realized in some materials. And here they're proposing, and there's some minor sort of, reasonably good implementations now to store data on it, okay? And the good thing here is that if we take existing realizations of maybe the best flash hardware, the number of bits that you store is roughly 10 to the 10 bits per nanometer, okay? So here you're measuring how much information can be stored in a unit of area, right? That's your metric. Whereas if I use DNA storage or DNA chemicals, then I get 10 to the 16 bits per nanometer. So it is much more efficient in terms of information storage, right? But this is still not violating PECTT because it's really in the constants, okay? You're changing the base constant, but it's not going to change in the long run, as the input scales, okay? So that's why this roughly S is saying that somehow I'm packing more information, but I still have to invest something to pack that information. And even though I'm packing more information, The rate is not changing. It's just the constant has changed. All right. But the most fun violation proposed, or potential violation that was proposed, was this. Do you know what this is? Does anyone know what this is? Or am I the only one old enough? Yeah? Doctor Who. And what does Doctor Who do? Time travel, right? So there's something called relativistic computing. Okay, and what is relativistic computing? Imagine, I built a machine which can travel very close to the speed of light, right? And what I'm going to do is I'm going to put that input and some time, put it in the machine, and travel close to the speed of light, and then do the computation on the other non-traveling thing, and then come back, right? Okay, so when you travel very close to the speed of light, time changes, right? So maybe 4 minutes here is equivalent to 400 years somewhere else, right? So I start the computation on the thing which is going to take 400 years, but on my space it's only 4 minutes. So did I violate PECTT because I computed the answer in only 4 minutes, whereas Boolean circuits would have taken long time to do it. And then as a potential theory, it makes perfect sense, right? I load up this machine, start the computation, and then it's traveling very, very fast, close to the speed of light. So time has dilated. So did I actually speed up the computation? Yeah? No, whatever, it went away. So on my machine, it's faster, right? In my view, it is faster. So the machine came back, and then after traveling close to the speed of light, and I see the answer. Maybe for the other person it's slow, but for me it's fast. But the answer should not be faster for any person. That's the claim, right? Okay, so what's the catch? No? Okay, so it's a very subtle catch, and the reason here is it says as physical resources. It doesn't just say time. Okay, and so when you try and do this, so imagine I want to run a computation on something that involves, let's say 1,000,000 bits. 1,000,000 bits is going to take some amount of mass which is proportional to the number of bits that you have. And to accelerate that to the speed of light, I need to spend resources which are proportional to that mass. Okay? So at the end of the day, you're still going to end up violating or not violating PECTT, because to accelerate to the speed of light, you have to spend resources which are proportional to the input size. We think of it as negligible, but it still scales at the same rate. Okay, yeah?
Just by curiosity, for the physical resources, if it contains multiple physical resources that are distinct, so how do we do the...
Yeah, so there's a lot of variability in here. So in some sense, you're giving anybody who wants, define your physical resources in some way, as long as, let's say energy, that's your physical resource. So come up with some plausible theory which violates it. And no one has successfully come up with one so far. Okay, there's one thing which does violate it, but we don't know if it exists. These are called, if you're very curious, I encourage reading about it. These are called closed time-like curves. Okay, I mean, don't ask me about it, but if you're curious, just look that up. I think it's interesting, and how it connects to PECTT and so on. Okay. But the key point here is everything that we think we can do, we can actually do with similar efficiency using Boolean circuits. Okay. So that's one reason why we focus so much on circuits. Okay. All of these 3 points, that they can compute everything, they are realizable by physical devices, we have a very efficient universal circuit, and we do believe that physically they're as efficient as we think is possible, consistent with our theories. Okay. Nevertheless, there are some serious drawbacks, and that's why the course is not ending now. We're not done with our computing models. We have a lot more to do. Okay. Any questions about circuits in general? We're not going to talk about circuits again until maybe the last 4 lectures of the class. Okay, when we talk about quantum circuits. Yeah? Like, basically, energy, for instance, saying something like, okay, I can build a computer, put it on a machine which is traveling close to the speed of light. Did I speed up the computation? Technically, you did speed up the computation, but you spent as much resources. Okay. Or you can say, okay, to spend that much physical resource like energy, you had to accumulate it over time. And that's where your time went. Right? In some sense, you pre-computed a lot of stuff to store back all that energy and then send this machine at the speed of light, let's say, or close to the speed of light. And that's how you sped up your computation. Yeah.
Like, let's say, with next to a black hole or something, frame, the computation is everything.
Okay. I mean, I don't think so, right? Because once you accelerated, so at least for this, for the computation to be useful, it had to come back to you, right? And then you had to check the result, right? So you can say obviously that you're, if you throw something into a black hole, maybe the information is lost forever, so you don't know what happened there, right? And yeah, this closed time-like curve is a very different beast. That's more interesting. Okay, this is basically like time travel, but you have a closed loop. Okay. Anyway, so it's very interesting philosophical thing, but we by and large believe that PECTT is actually true, with one twist that we'll talk about in the end. Okay, instead of Boolean circuits, let me say that you have to replace Boolean circuits have 3 things: and, or, and not. Okay, to get to what is consistent with every physical theory that we currently have, you need to add 1 more gate to the mix. If you have 4 gates, then we believe this is true. And we'll talk about that much later. All right. So that's all I wanted to say about circuits. But there's still a lot to do, and we'll talk about the main drawback of circuits and why we need to look at other models after a short break. Let's take a break now because we're going to end circuits, and then when we come back, we'll talk about why circuits are still limited and what to do about it. Okay? Okay, so what's the problem with Boolean circuits, right? I mean, even the fact we do have very, very good properties, right? But by and large, the biggest problem is that they are defined for a specific input size. Sounds like a very mild annoyance, but it's a really fundamental issue, okay? So what do you mean by that? Here's kind of a cartoon explanation of the problem. This is what circuits feels like. Today we're going to learn how to multiply 1-digit numbers, tomorrow 2-digit numbers, tomorrow 3-digit numbers, after that 4, and so on. Okay. So the analog of this is for circuits, even though we have a single eval, NMS, and so on, right? But it's different for each possible input length, right? So it's not like an algorithm. I have to build a different circuit when I'm multiplying 3-bit numbers. When I'm multiplying 4-bit numbers, I have to build a different circuit. When I'm multiplying 5-bit numbers, I have to build a different circuit, and so on and so forth, right? So on the other hand, when we think of the algorithm for grade school multiplication, it's a single algorithm which works for every possible input length, right? And in the same way, when we think of building a computational model, we don't want to limit the input length. If you were allowed to limit the input length, then Boolean circuits are it. We can do what we want, right? But as I said at the very beginning, we are interested in building a model or identifying a model which is kind of time invariant, right? So maybe today you're only interested in handling, strings which are 10 bits long. Right? 10 days down the line, maybe you're interested in handling strings which are 11 bits long. Okay? Maybe 10 years down the line, you're interested in handling things which are 100 bits, and further, maybe after that, 1,000 bits, and so on and so forth, right? And this has been happening throughout our history, right? Back in maybe a long time ago, not too long ago, like programs would only be a few KB, but now they're MB, now GB, and so on, right? So the size is not bounded, okay? Whereas our computation model has the limit baked into its own definition. There's no way around it. I have to tell you what the number of inputs is upfront before I even define the computational task, and then also what the computational model is. Okay, you can say, oh, that's easy. I would just give a different circuit for n equals 10, different circuit for n equals 11, n equals 15, and so on and so forth, right? But then the problem is, how do you know which circuit to actually implement? When n changes, when the number of inputs change, you need someone else to tell you how the circuit changes, right? You gave me the wiring for 15 bits. Now I have to do it on 100 bits. How does the wiring change? That has to be specified. But you want that also to be automated. Okay? So that's the fundamental limitation of circuits. So we want okay. So they operate on inputs of finite length. For example, I cannot say, okay, give me a circuit which captures grade school multiplication. I can only give you a circuit which captures grade school multiplication on maybe 10-bit numbers, maybe 11-bit numbers, 15-bit numbers, but not for the algorithm itself. Okay? So if you want a model which is going to really stand the test of time, this is not it. You have to come up with something else. Okay, does the problem make sense? What the issue with circuits is? We really want something which can scale up irrespective of the input length. And their circuits fall really short. Yeah? So that's a very good question. The issue is that eval itself has the n, m, and s inbuilt in it. So for every possible input length and for every possible size, there's a different eval circuit. So if I give you a chip which can simulate all circuits of certain size, but it only works for inputs of length, let's say 100. You can massage it to say, okay, it'll work for all size, all inputs up to 100, but it's not going to scale to 1,000. Maybe tomorrow I'm interested in 10,000, then this chip is useless even as a description. Okay, so that's where circuits are limited, right? Okay, so what we'll do is to tackle this challenge and come up with a different model, and later on you can use that to even fix the Boolean circuit model to make it time kind of the input length unbounded. Okay, but first we need to address this question of how do we handle things where the input length can grow. Okay, to be concrete, let's start with a very simple task. So we looked at XOR 2, XOR 3, and so on. And we saw that, okay, XOR 2 can be computed by Boolean circuit, XOR 3 can be computed by Boolean circuit, and so on. Now let me just define general XOR. Okay. It takes an input of any length and outputs 1 if the number of ones in the input is odd and is 0 otherwise. A very simple function. Okay. And if you ask me or anybody else, you'll say, okay, this is a very easy to compute function. I can write a simple program for it. Okay, so here's a simple program for computing the XOR function. You start with 0 for every bit that you read, check if it changes the parity, and then return the final answer. Okay. But our Boolean circuit model cannot capture this. Right? So they cannot capture any such algorithm because here the input length is not limited. All right? So we have to somehow get around this obstacle. And the way we will do it is to come up with a very simple, model which can do this. This is kind of a caricature, and then study its properties, and then fix it to get the fully general model of Turing machines towards the end. Okay? And the model that we're going to focus on now is they're called deterministic finite automata, or DFAs. They have very, same thing with different names. They're also sometimes called finite state machines. Okay, but we'll mainly stick to DFA. Okay. So the way to picture a DFA is take this algorithm for XOR. So what is it doing, right? So I can imagine my state, which is, okay, answer equals 0, answer equals 1. Okay. So what is this algorithm doing? You start from 0. Okay, here's where I start from. And every time I see a bit, I do something, right? So I read x0. If it's a 0, then my answer doesn't change. If I see a 1, my state changes to answer equals 1. Okay? And if I see a 0, my answer doesn't change. If I see a 1, it changes here. Okay? So this diagram is basically the same as this algorithm. Okay? And the good thing about the diagram and the algorithm is it's independent of the input length. Right? So when we think of a program or an algorithm, you should really think of it as something which is a solution to an infinite number of problems. no matter what input string you give, the same algorithm is going to give you the answer, right? So here, the description length doesn't depend on whether my X is 1,000 bits long or 1,000,000 bits long. It's the same algorithm, right? So that's what we want to capture. So this diagram, what it does, doesn't depend on what's the input length you are going to feed into it. It's still, the description is independent of the length, but it'll give the right answer no matter what string you give. Okay? So that's what we are shooting for. And as a toy model, this DFS are very useful in that regard. Okay, so let me formally define deterministic finite automata. So you can think of DFS essentially as, I mean, if I were to describe in one sentence, they are fixed memory, single pass algorithms, meaning you have a fixed number of states that you can, be in, fixed number of bits that you can somehow store. And every time you see a bit, you do some processing on it, and then you forget that bit. Okay, so you just make a single pass on your input, right? It's a very limited model, but it's okay. As a start, it's fine. Even as a very limited model, it overcomes the drawback that we had with circuits, which is that they were limited in input length, whereas this model isn't. Okay? So the formal definition is a little bit verbose, but it's, let's do that for once. So a DFA with, we'll say, C states over 0, 1 is a pair which will write as T, S. Okay, where T I'll explain what this means in a second, where T, or the transition function, it's like a table. It takes a state name. This is the set 0, 1, 2, all the way up to C minus 1. Okay, and a bit 0, 1, and tells you what state you are going to go to. Okay, and S, the set of special states, is some subset of C. And again, this is shorthand for 0, 1 through C minus 1. Okay, and you should interpret T as saying, if I'm in state I and I see bit A, then you go to bit J. Okay, so just imagine that a DFA is basically like a hopping machine which has C cells, C squares, each number from 0 through C minus 1. You start from somewhere, and according to the transition diagram, you keep jumping around. Okay, I'm in state number 17. I see bit 0. I look at the table T. It tells me you have to jump to state number 34. So I go there. Then I look down. I'm in 34. The next bit is a 1. Then it says, okay, jump to 41. You jump to 41, and so on and so forth. Okay, you forget how you got there. You just look at where you are, look at the next bit, and then take the corresponding jump. Okay, so you should think of T as some kind of table. Yeah, actually, right? And the computational model associated with it is very simple. So every DFA now, I can associate a function with it, and it's as follows. On input X, Okay, so just for convention, I'm always going to start from state number 0. Okay, as I said, really imagine right. So these are numbers 0, 1, 2, all the way up to c minus 1. Okay, and I always start just by convention from 0. You can also say, okay, you start from somewhere else, but let's minimize the number of moving things. So you always start from 0. And then t tells you, if you see a 0, you jump to maybe 2. If you see a 1, maybe it says you go to this one. Okay, and similarly, for every node, you might have something like this. Maybe this is a self loop. Okay, so when you on any input x, no matter how long it is, you always do the same thing. You start from a state, as 0, and then for each of the bits, you define the next state as what you get by taking the corresponding jump. Look at where you are, you read the next bit, and you take the jump to where the table points you to. Okay, t tells you where you have to hop to, and you just take that hop. All right, and in the end, you output 1 if the final state is a special state. Okay, and you output zero otherwise. Okay, so you have some special states, which is part of the description of the machine now. And you take all of these hops as dictated by the thing, and maybe there are some special states, like this is special, then this is special. If you end up in one of the special states after reading all of the input, you say 1, otherwise you say 0. Okay, very simple computational model. But as I said, even as simple as it is, it already overcomes the limitation of being able to handle any input length. Okay, it's a finite description which is independent of the input length, and it can compute something. Any questions about the definition? Okay, and then just as we did before, we can say a DFA computes a function if on every input the output of the function is exactly the output of the machine. Okay? Yeah?
Onto the screen, and with the star thing, means we can get empty string as well.
We can get empty string as well. So empty string just means that by convention, you will just output whether or not where you're starting from is a special state or not. Yeah, that's a good question. I'll make it clear in a second. Okay? Yeah. Right. So let's see an example. Okay, so we already defined XOR, and we said, okay, the algorithm that we saw can be captured by this diagram. Okay, so this is essentially going to be my state machine. I'm going to put 0 here, 1 here. So the number of states is 2. Okay, and the t is given by these arrows. What should S be? When should you accept? What states should be special states? Yeah, 1, right? So we will always denote in diagrams, we'll denote special states by like this double ring. Okay, saying, that's just convention. Okay, or to make it visually easy. And just to be precise, I can write down what the t is fully. So if I'm in state 0 and I see bit 0, I go to state 0. If I'm in state 0, I see bit 1, I go to state 1, right? That is this arrow. If I'm in state 1, I bit 0. If I see bit 0, I go to state 1, which is this arrow. And lastly, 1, 1 takes you to 0, which is this arrow. Okay? Right? And I said, there are different names for the same thing. These are called state machines, deterministic finite automata, finite state machines, state space models. They're all the same thing. Okay? And as you say, these get used a lot. Can you give me an example of a DFA that you came across today? No? Yes? In the real world, my claim is that every one of you encountered a DFA somewhere. Yeah? I think it's worse than a DFA, but yeah, kind of the same thing. Something even more physical. That's more complicated. This is a DFA, right? What does it do? It has kind of two states, locked or unlocked. If you're in locked state and you press the lock button, you stay where you are. If you're in an unlocked state and you press the lock button, you go to locked, right? So this is a physical implementation of a DFA. What else? Because nowadays cars come with cards, but at least this one comes with a DFA. Elevators are DFAs. Depending on what state you are in and what input up or down or the elevator level, you go to somewhere else. It doesn't remember, how you got to that particular floor, right? Just based on the input, it goes somewhere else. Okay? And there are lots of examples like this. So state space coding actually plays an important role in many of these control systems. Okay? All right. So, and if you're looking at some other resources, usually DFS also come with other stuff, like you can specify where you start from. But I think, since we're only interested in the main properties, I'm trying to minimize notation, and we'll just adopt the convention that you always start from 0. Okay? And technically speaking, we are looking at DFAs where the alphabet is 0 or 1. Okay. Meaning I can also define it where I have more things, 0, 1, 2, and so on and so forth, but it's the same model really. Okay? All right. So let's do a few more examples. And then we'll start talking about, what are the properties of this model, what can they actually compute, and so on and so forth. Yeah? So here. So basically, what are the ingredients in a DFA, right? So to tell you what a DFA is, I have to tell you what this transition function is and what are the special states. That's it. Okay. Once you tell me these two things, you have effectively defined to me a computational model, a machine which can process inputs of any length. And it does a very specific computation. Like, for example, if this is my T, let's say, and my S is the set of just 1, then it computes the XOR function. Okay? And if I change my S or my T, I might get something else entirely. Okay? By changing T and S, I'm computing very different things. And the main thing that we're gaining here by switching over from circuits is that the description length is independent of the input length that you're processing. Special states. S is the set of special states. Basically, it's like, I keep hopping around on this, like a, what's the game where you dance on the floor? No, the one you see in arcades. Sorry? Yeah, exactly. It's basically like that. You're hopping along that according to some instructions, and in the end, you win or output 1 if you're in one of the special states. Right? Okay?
With the information, we need to be able to design a DFA, or we need to be able to figure out if they're giving the state, we're gonna figure out.
So a bit of both. Ideally, if I want to compute a function, I want to first figure out, is there a DFA to compute it? Okay, if it is, then I can talk about, okay, can I actually implement it some way, and so on and so forth, right? But it's a very simple model, right? But it still sounds reasonably useful. You're going over the entire input, and you get an output. And the description length is independent of the input length that you're processing. Okay, yeah? The alphabet is, basically, if you follow some other text, you'll see that DFAs also come with this notion of alphabet, where instead of 0, 1, I can have like ACGT and so on. So yeah, exactly. So, but I just wanted to stress that we're only looking at 0, 1. So if you see something else, don't get confused. It's really the same thing. I'm simplifying the notations really. Okay. Yeah. So let's do a few more examples. Now I'm going to draw a picture, and you have to guess what function is computing. Okay, so this is just this dangling arrow is meant to denote that you're starting from there. S equals 0 says there's only one special state, which is 0. And to be absolutely precise, you can really describe it either by a diagram or by the transition table, right? So you can say state, bit, state. Let me do this for once, and then from now on, we'll only draw diagrams whenever possible. So if I'm in state 0 and I see bit 0, I stay there. 0 and 1, I go to 1. 1 and 0, I stay there. 1 and 1, I go to 2. 2 and 0, I stay there. 2 and 1, I go to 0. Okay. So what function is this computing? Yeah. Yes, exactly. Right. So what's happening here, right? Every time you see a 1, you jump to the next one. Like, if you're in 0, you go to 1. If you go in 1, you go to 2. But then you circle back to 0 once you have seen 3 ones. Okay. So what does this mean? The function it's computing is d of x equals 1 if the number of ones in x is 0 mod 3 and is 0 else. Okay. All right. And okay, let's do one more example. We'll do a few examples to kind of get the hang of this. And then we'll start addressing abstract properties. Now I'm going to define a function, and you have to tell me what the DFA is going to be. So I want to compute the function, which is 1 if the number of ones in x is 2 mod 3 and 0 otherwise. How can I get a DFA for computing this function? Any suggestions? How many states do I need and what do I change? Yeah?
Like saying, if it has a force, change the acceptance state to
Exactly, right? You know, I can just really take the same thing, but change my accepting states. So I didn't change the t at all, right? This is a transition diagram, transition function, and this is not changing at all. I'm only changing the set of accepting states, and that completely changes the function, right? So now I only declare victory or accept the input when I'm in state 2 as opposed to state 0. Okay? Okay. Let's do a couple more examples. So my next one is the following function. Right? So now I want to compute the function which checks if x ends in 1 and is 0 otherwise. How can I compute that using a DFA? Yeah? Okay.
If you take 0, we're saying if you take 1 is the answer.
Okay.
If you
Okay. Yeah, I think this works. So what's happening here is, basically think of some meaning for this state, right? So you say this state, its conceptual meaning is that the bit just seen is a 0. Okay? And this says that the bit just seen is a 1. Okay? So if I'm just trying to remember the bit I just saw. Okay? If I see a 0, I remember 0. If I see a 1, I remember 1. That's it. Okay, very simple. All right. Now, okay, we can be a little more tricky. I think so far things are not very surprising, right? You know, DFAs, you keep reading the input, you remember something, and you keep hopping around, and then you're fine, right? So the next function I'm interested in is f of x equals 1 if first and last bits are the same and 0 otherwise. Okay. So meaning, for example, f of 1, 0, 1 is 1, f of 0, 1, 0 should be 1, f of 0, 0, 0, 1 should be 0, and so on. Okay. So I'm asking whether or not there is a DFA that can compute this function. The first and last bit are exactly the same. Any suggestions? Yeah? Okay. Can you compute it with the DFA or not? Somehow it seems a little bit more tricky, right? Because you need to remember first and the last bit. But you can only remember a finite number of things irrespective of how long the string is. Yeah?
Like, if we saw one, and then whatever in between we get, we can like move around and we mark when we saw the last one.
But how do you know when this is the last bit? You have to a little bit, you don't know what is going to be the end until you reach the end, right? So if you remember, if you discard it, you might be in trouble. Yeah?
Do what you did in the previous problem and like say you start at a state 0, and then if you go to 0, say you go to like state 1, and then regardless of what you get, you stay in state 1 because that's not your special state, and then you have like a state 2, which you can attach that to state 2 and just use the same logic.
Yeah, I think that works. Let me just maybe simplify a little bit to make the idea clearer. It's going to be less efficient, but I think that works. So the suggestion was somehow, so here we're already remembering kind of which was the first bit, right? So what I'm going to do now is use the same idea, which is, and I'm going to give them different names.
Oh, congratulations.
But the same arrows.
End of November?
Okay. So I'm going to start here. If I see a 0, I'm going to branch.
Wait, where are you going?
If I see a 1, I'm going to branch. Okay? So based on whether or not I see a 0, I need to remember, is the last bit going to be 0 or the last bit going to be 1? Okay? So here, this entire segment is trying to say, okay, we remember that the first bit is a 0. And remember, first bit is a 1. Okay? And then we redo. So if you see a 0, you do this, and so on. And let's call this 3 and 4. Right? And what should be the accept states in this diagram? 1 and 4, yes. Okay? Yeah?
Shouldn't you make the end state because we just
That's a good question.
but
First,
like 3 would have 1 point to itself.
Right. So that's a good question. So this almost works, right? Except for the case when there's a single string. If it's a single one, this doesn't work. But other than that, everything works, right? So let's fix this a little bit. Okay, so it's almost works, except if x equals 1. Okay, then we are in trouble. So I'm going to copy this and slightly change the edges. Okay, and the way I'll do it is basically change these names, really. Okay, so I just flipped the roles of 3 and 4 and connected it this way. Yeah,
If we get an empty string, the first and last is gonna.
that's a good point too. So then we have to add this guy. Okay, so by convention, empty string means that you have to accept because the first and last bit are technically the same. So we make the starting state always accept. Okay, and this empty string thing is like a convention. So the problem has to say, okay, first and last bit are the same, means this has to be true. Okay, any other questions? So my claim is that this DFA with 5 states exactly computes this function. The first and last bit are the same. Okay, I mean, it should not be shocking, but it's still a little surprising that somehow I can skip everything in between and still compare the first and last bits with only finite amount of memory, right? This is not, you can make it more efficient by having something with fewer states, but in most of the time, we're not really interested in optimizing the number of states that you use, okay? Because we're really interested in the fact, whether or not I can compute it with a fixed number of states, something that doesn't depend on the input length, okay? All right, and so let me add this remark. So 0, 1 star by convention has the empty string. Okay, really doesn't change what we compute or the meaning of the definitions, but this convention we have to stick to something, and it is helpful for later compositions that we will do. Okay. And this empty string is usually denoted as epsilon in the literature of DFA. Okay, let's do one more example. Okay, so f of x is 1 if bits are alternating and is 0 otherwise. Wow, my handwriting is getting worse and worse. I'll try to write things more clearly. Okay, so if the bits are alternating, you have to output 1, otherwise you have to output 0. So if 0 is 1, f of 1 is 1, f of 0, 1 equals 1. And so on and so forth. Okay. So any ideas on how to compute this using a DFA? In sessions. So in some sense here, one thing you can exploit is if I see 2 consecutive things which are the same, you should basically reject it, right? You should output 0 at that point. Starting state is an except because, by convention, an empty string is, essentially alternating. Okay. So you can imagine what you have think as a machine, right? So if I see a 0, I do something. If I see a 1, I do something, right? And you can try and remember what the computation needs, right? So I have to remember the previous bit, and other than that, it's okay to forget. Okay. So you have a suggestion for?
You have like one state which is like the previous bit was 0, one state where the previous bit is 1, and another state where it's like that it wasn't alternating, and if it wasn't alternating, extend it to that state.
Exactly, right? So that's what I think that should work. So I start from the state 0. And if I see a 1, I go here. Okay. And effectively, this is meant to say bit seen is a 0. And this is bit seen is a 1. Okay. If I'm in a state where I see a 0 and then I immediately see a 0, what should I do? No, because if two things are same, then you have to reject, right? So you go to like a different state, which is kind of a graveyard, meaning you're not going to get out of there. It's like a dead state. You're just going to loop there forever. Okay. If I see a 1 here, I go there. Okay. Then if I see a 0, I go here. See a 1, I go here. All right. And what should the accept states be? 0, 1, and 2. All right. So you can play around with how to come up with this DFA for specific functions. We'll do that to a little bit. But for the most part, we will pretty soon be interested in, again, abstract properties. What can we do with them? Can I compose them in some way? And other meta things. Yeah?
Have the state 0 to be the final state? Is it because for the empty string?
Yes. Yeah, that's the only reason. Okay. All right. Let's stop here. And when we come back, we'll continue our discussion of DFAs on Wednesday.